All right, class, we'll get started. So welcome back. We only have a few lectures left this semester, so we're zooming towards the very end. Just a few announcements. So first, the Student Advisory Committee is requesting input. So there's a couple things. This is the anonymous suggestion box. You can either use this QR code. I think it'll send you straight to this link, so you can use this link as well. And then as a department, we're also working on putting together new emphases in chemical engineering. Right now, I think energy is our only one, but we're looking to put together some new ones, like in the bio area, for example, is one that I'm working on. So if you have any suggestions for the types of things that you'd like to see represented in the new emphases within the department, at least for the next generations of students, then please add your suggestions at that link. And then there's a unofficial student group me as well. And so this QR code will take you to log into that. And the Student Advisory Committee is asking that you sign up for this. So I'll send this out to the class as well as an announcement, so you have all these links, because I don't think these were in the slides that I put out yesterday. But yeah. Okay, so some class announcements today. So homework 10 is due Wednesday. Homework 11, which is the last homework that we have in the class, because we're just about out of time, that'll be assigned on Wednesday. As a reminder, your final project is due on 12/7 as well, the same time that homework 11 is due, and that's the last day of class. So make sure you're working on those as well. Final exam will be December 12th. Sorry, what was that? Final exam will be December 12th, 8 a.m. in this room. Yeah, just keep that in mind. That's coming up too. Any questions on any of this? Any questions on assignments or anything before we get started for the day? Okay. All right. So where we left off. So we're talking about compressible flow, right? So we're in chapter 9 now, talking about flow where the velocity, the relevant velocity is comparable to the speed of sound, right? So typically we say that we're in the compressible flow regime when Mach number is greater than what? What's our critical Mach number for having to consider compressibility effects? 0.3, right, is our critical Mach number for having to consider compressibility effects. We saw, for example, that in liquids, the speed of sound is typically really high, right? So typically we're not anywhere near the compressible flow regime in liquids. But in gases, we often can be. Yeah, and in this regime, we will occasionally have shock waves, and so we're going to start talking about shock waves today, really continuing on Wednesday as well. But first, we have to finish off our discussion on compressible flow through a constriction. And one of the things that we discussed at our last class on Wednesday last week was that things get a little bit weird when we have compressible flow through a constriction or a throat, right? So when we have compressible flow that comes to through some narrowing of a duct, then things can get a little bit weird. So just as a reminder, we're now considering the case where we have flow through a variable area duct, like is shown in the upper right-hand corner there. It will sometimes be the case, and we'll put more concrete conditions on that we can end up with subsonic flow on one side and supersonic flow on the other side. In that case, when we have subsonic flow on one side and supersonic flow on the other side of that kind of a constriction, what we showed last week on Wednesday was that the Mach number must be equal to 1 at the local minimum of the area of the duct. Right, so if you didn't see that, or if that's not ringing a bell, make sure you go back and review that. But we showed that the Mach number must be equal to 1 at the minimum if we have subsonic on one side, supersonic on the other. And this having that limitation that the Mach number is equal to 1 at that throat actually places an important limit on the mass flow rate through a duct with with a variable area when we have compressible flow. So let's so to get there, we're going to start with mass conservation. So based on mass flux through this system, if we have a flow through some system with variable area, we know rho VA, right, is going to be the same everywhere across every cross section. So that means we know that rho VA is equal to, right, at any place within this duct has to be equal to rho star V star A star, where star means the value of those quantities at the throat itself. All right, so we can put the mass flow rate anywhere within the duct has to be equal to the mass flow rate through that throat. And at that throat, we know Mach number is equal to 1, and so this will be a little bit convenient for us. So using the relationships that we developed for a perfect gas, right, again on Wednesday of last week, we can rearrange those. Again, assuming no shocks, so assuming that for now that we have isentropic flow, we can then write out this expression where we have A over A star is related to Mach number at wherever we have this section A, K, right, the specific heat ratio, 1.4 for air, and here's Mach number again. So A over A star is really for a given gas, right, which has specified K, is just a function of Mach number. Okay, so so for example, for air, if we plug in K is equal to 1.4, we have this expression for A over A star. So this means that if we have a duct where we know what the area is at the throat, if we know what A star is, and if we know what A is, we know what the area is at a given location, then we can use this expression to figure out what the Mach number at that location is. Okay, so if we know this ratio, if we know, for example, how big, if we know A star and we know A, or even if we just know this ratio, how big A is relative to A star, how big the area of a certain section of the duct is relative to the throat, then we can use this expression to solve for or to figure out what the Mach number is at a given location within the duct. So this can then allow us to solve for Mach number as a function of A of X. And then once we know Mach number, or if you remember from Wednesday, if we go back and review from Wednesday, once we know Mach number, we can use our isentropic perfect gas relationships to figure out the pressure, density, and speed of sound and everything else that we need to know about the flow, plotted again here, right? So here we have A over A star, P naught over P, rho naught over rho, T naught over T, plotted as a function of Mach number, right? So remember where we were last time is that we developed a set of relationships that allow us to figure out pressure relative to stagnation pressure, density relative to stagnation density, temperature relative to stagnation density, temperature rather, sorry, in terms of Mach number. With this expression, we can find Mach number based on area, right, based on the area of the duct. And so putting this all together, it means that if we know the area of a duct as it changes shape, then we can use these relationships to now step through and solve for all of the different variables that we might want to know. Okay, this is going to be central to how we solve problems for variable area ducts. So you can use, for example, this expression. You could use this table, I guess, this chart if you really wanted to. You could use this equation and the equations that we wrote out on Wednesday, which are reproduced here. Or you can also use these compressible gas tables in order to do this, to solve this kind of a problem. So This is table B.1, B.1 in the back of your text. This is something that I'll give you on the exam, okay? Not something that I expect you to have or necessarily bring for yourself. But with this table, you can then, very quickly, for example, if you know Mach number, or if you know the Mach number is 0.5, you can now find pressure relative to stagnation, density, right, and temperature relative to stagnation, A over A star, and work your way through a problem using this table. Yeah. No, the table is really just tabulated form of these equations. So you can use these equations as well if you want. But for example, you might, these equations are written in so that you have, rho naught over rho as a function of Mach number, right? But you might, or for example, this is a good one, right? You have A over A star as a function of Mach number, right? So if you know Mach number, you can find A over A star. But it will often be the case that you actually know A over A star and you're trying to find Mach number. And so you have to go in the opposite direction. So with the table, it's just easier to go, in either direction if you want to, right? And I would suggest interpolation. If you have a over A star value that's not exactly equal to one of these, then you would want to use interpolation in order to figure out, what, for example, the Mach number is.
Are we assuming linear relationships?
I would just use linear interpolation. Between any 2 points, I would assume linear, right? We know this is definitely nonlinear. These relationships are decidedly nonlinear, but between any 2 points, these are close enough spacing that we could use linear interpolation. Okay, so this is going to be when we know that we have adiabatic isentropic flow, which in this class primarily means we have flow without shock waves, right? So we're not considering compressible flow with heat transfer. That's going to be beyond the scope of what we cover here. But you do have to understand whether or not there are shock waves, because a shock wave is not isentropic. We're going to deal with that, but shock wave is not isentropic. So when we don't have a shock wave, we have flow through a variable area duct. These tables or these equations are going to be your friend. But I want to talk for a second about, so any questions on this before, when it pops back up, hopefully? Okay, there we go. Any questions on this before we move forward? Yeah. Well, I haven't written the exam yet, so I don't know. You'll have some previous exam problems where you'll see. It could be the case. It could certainly be the case where you're given, what the area is, and you're trying to find the Mach number, right? Because you have some duct of known shape, right? But it could also be the case that you're trying to design a duct to achieve a certain Mach number, right? In which case you're trying to find the area to get to a certain Mach. So it could go either way. Yeah. One other thing I want to draw your attention to before we actually move away from this, I'm actually just going to go back one slide. If you look at this A over A star, you'll see that for a given value of A over A star, there are actually two solutions. There's a solution for a Mach number less than 1. If we follow over this A over A star of 2, there's another solution for Mach number greater than 1. Okay. We'll look at where this comes from as we talk our way through some converging, diverging novel problems, but it's something I want to draw your attention to before we move away from it. That this reflects the fact that when we have subsonic flow, as we decrease area, what happens to the velocity? Does it go up or down? In subsonic flow, we decrease area, velocity goes up or down. Just give me thumbs up or thumbs down. I see a lot of thumbs up, yeah. Because in subsonic flow, as we decrease area, the velocity goes up, right? Now in supersonic flow, when we decrease area, what happens to the velocity? We decrease area in supersonic flow, it goes down, the velocity. Yeah, which is weird, right? This is one of those weird things about compressible flow, and that's reflected here, right? So the way that we increase our velocity in supersonic flow is by increasing the area, right? So as we once we cross this Mach number equal to 1, if we want to increase Mach number, right, increase velocity relative to local speed of sound, then we have to actually increase the area. And so you'll see on the table, there's one thing to be aware of. You'll see on the table that at Mach number equal to 1, A over A star is equal to 1, right? Because A star is the area where Mach number is equal to 1. Right? But it increases, A over A star increases on either side of this point. So in order to solve a problem using these tables, or even to use using these formulas, right, you have to know whether the flow is subsonic or supersonic in the first place. Okay. So you have to know if you're on the subsonic side of the throat or the supersonic side of the throat. Yes. Yeah, so if you have row over row stagnation, right, you can see it just always decreases, right? So there you don't have to worry about that. Yeah, that's right. Okay, so let's talk for a second about something else that's a little bit strange about supersonic flow. And this is what's called choked flow. So it's kind of like a punny name, right? So we said that the minimum area we call the throat. And when the Mach number is equal to 1 at the throat, we call the flow choked. And the reason we call it choked is that the fact that Mach number has to be equal to 1 at the throat sets a limit on how much mass you can actually get through a duct in compressible flow. All right, so you can't increase the Mach number at the throat. Right, it can never go higher than 1. So that means that the condition where we have Mach number equal to 1 at the throat, that is the highest possible mass flow rate that we can get through a duct for given inlet-outlet conditions. For a given stagnation pressure, the maximum possible flow through a duct is when its throat is at Mach number is equal to 1. And this is regardless of what we do at the exit. Right, so now let's just think back to a second from incompressible flow, like what our intuition would be. Like if we have a reservoir at a certain pressure, and we're trying to drive flow through some duct to some outlet, right? If we decrease the pressure at the outlet, then we'll increase the overall pressure difference from inlet side to outlet side, and therefore increase the flow rate, right? What this is telling us is that at some point, when we get to once we get to the condition where Mach number is equal to 1, if we have some constriction, and once we get to the condition where Mach number is equal to 1 at that constriction, we could keep decreasing this outlet pressure, and the mass flow rate through the duct will stay the same. That's what choked flow means. We'll look at that in graphical form in a more concrete example on the next slide, but choked flow is another one of these kind of strange non-intuitive consequences of compressible flow. So when the throat is at Mach number is equal to 1, well, we say that the nozzle or the duct is choked. Okay, so that's what that nomenclature means. So increasing flow would require the throat to be widened. Yeah. If we have Mach number equal to 1 at any throat, we say it's choked.
But not every throat has Mach number.
Not every throat will have Mach number equal to 1, right? We can have a throat that is subsonic, right? So if we have not yet achieved the Mach number equal to 1 at the throat, then we can have a subsonic throat. We're very rarely going to have a condition where we have a supersonic throat. So when throat is at Mach number equal to 1, nozzle is said to be choked. Increasing the flow requires the throat to be widened. So this means that, for example, other changes to the shape of the nozzle, right? So you might have like a rocket nozzle or something, and you have some outlet flare that you're using to try to control the flow. If the flow is choked, then other changes to the shape of the system will not affect the flow rate, right? And this is also a little bit strange from our incompressible flow intuition. So for example, like Formula SAE competitions, like in college competition to build a race car, they will often restrict the intake throat diameter for this reason, right? So that way you have a maximum mass flow rate that everybody is limited to. So we can use our relationships we saw on the previous slide, we showed on the previous slide, in order to find the maximum mass flow rate for compressible flow through a choked throat. So say m dot max is just going to be rho star, a star, v star. And we can solve for these things. So in this case, it's so this is comes from our rho over rho naught expression. We can plug in our a naught expression, and then v star. This is going to be equal to the speed of sound, essentially at that throat. That's where this comes from. And so from that, we can write an expression for m dot max. And if we plug in this for k is equal to 1.4, we'll end up with m dot max. And we'll see it's a function of stagnation conditions, right? P naught and T naught, and A star, but nothing downstream. Okay. So for example, exit conditions do not come into play here. So the maximum mass flow rate that we can get through a throat of a specified area is just a function of the upstream conditions, not the conditions downstream. Right, so those are stagnation conditions, P naught and T naught. So one potential example of this is, let's consider that we have a flow through some pipe with a valve, but now let's consider the case of compressible flow, right? So not last chapter we dealt with this, or 2 chapters ago we dealt with this. This actually comes from your textbook in chapter 6, is where this image comes from. And we talked about primarily liquid flow. We confine ourselves to incompressible flow through ducts in that chapter. But now let's talk about what can happen in this case if we have compressible flow through such a pipe with some kind of a partially closed valve. All right, so we have a run of air or gas pipe, and someone forgot to open the valve up all the way. So now what's going to happen if we look at the operation of that? So let's say that the upstream pressure, we'll call that P naught. Let's say this pipe is coming from a large tank at some stagnation pressure P naught. That upstream pressure is constant, and we're somehow reducing the downstream pressure. We have a regulator on the system, and we're reducing the downstream pressure at P2. So this is what we would expect. So if we look at m dot versus the difference in pressure, in this case, the square root of the difference in pressure, we might expect from our chapter 6 relationship that we would be able to find, for example, the head drop across this whole system this way. From this, we can find the pressure drop, right? Head drop is just P over rho G, delta P over rho G. And so, and then based on the velocity and the density and the area and so on, we can then find our mass flow rate. And we would expect that as we increase the difference in pressure, as we increase the driving force, we're going to see a continual increase in the mass flow rate through this system. And this is true to a point. But at a certain point, this is going to flatten off. And what is this condition here? When we've flattened off, what do we say has happened? We're choked, right? So this is true up until the point where this constriction becomes choked. So when that constriction becomes choked, if I keep decreasing my outlet pressure, I keep increasing the driving force across this pipe, the mass flow rate does not increase past a certain point. Okay, so at this point, we said the flow is choked. At this condition, what's the Mach number right here? 1, right? Because the flow is choked, and so the Mach number is 1 right here. Okay. So what's going on here? So this is choked flow. So for example, at this valve where we have a local minimum and area, we would expect the Mach number is equal to 1, and therefore the flow rate doesn't increase any further. Okay. Any questions on this? This is a little bit counterintuitive based on what we've learned previously. Okay, we'll get some practice on. Yeah, you first. Okay, yeah, so does Mach number equal to 1 definitely mean that there's supersonic flow? There is one condition in which it would not necessarily be supersonic flow, and we'll look at that in an example, in the next couple of slides. Okay, so we'll talk through what will happen. We'll talk through in a little bit more detail what happens as we decrease that outlet pressure. In just a couple of slides. But that's a good question. Almost always, it's going to mean that we have supersonic flow downstream, but there is one case in which not. Yep. Yeah, so is it true that the more shut the valve is, the more likely that the flow will be choked? Yes, that's true, right? So you can think of it in terms of a mass flow rate condition, right? Like there is, for a given, let's see, there is a maximum possible mass flow rate through the system. And for given stagnation conditions, right, like P naught, T naught, like our upstream tank is at P naught and T naught fixed conditions, right? So that means that for smaller A star, right, there is a lower M dot at which the flow becomes choked. So what we would see is that as A star decreases, the line where this thing splits off would get lower and lower and lower, right? Because there'd be we'd hit that M dot where the flow becomes choked earlier. So yes, that's correct. Yep. Other question? Yep.
Yeah. So first, does that decreasing the outlet pressure does nothing to
Yeah, once we've hit this condition.
So does that like create shockwaves or something like that? It goes through?
It's a great question. So does that create shockwaves as it goes through? And the answer is yes. So and actually to maybe complicate your question about what happens downstream, do we always have supersonic flow downstream? The usual case is that we have supersonic flow at least immediately downstream of where the throat is. But as we get further downstream, we'll see that we can get shock waves that then jump the flow back to subsonic flow. And we're going to talk about shock waves. We're going to have to talk about shock waves pretty soon. Okay. But yeah, so one problem here is that if we have flow through, we have choked flow, and we now have supersonic flow downstream. Now that supersonic flow exits into atmosphere that's still, right? So at some point, the pressure of the gas that's coming out has to match the pressure in the atmosphere. And the way that pressure matching is enforced is through shock waves. And we'll look at that. Okay, other questions? Okay. So just a few notes on nozzle flow before we move on. So we can find the A over A star, right, as a function of Mach number. So if we know P naught and T naught, we can figure out what the maximum mass flow rate is, for example, through a duct. But if we know where our, but let's say we're given a problem where we have some variable area duct, and we know the conditions, the pressure, the temperature, or let's say we just know the Mach number at a certain point. We know the Mach number at a certain point within a duct of variable area. Let's see if I have a marker. Of course not. So if we have a duct of variable area and we know the Mach number at a certain section of that duct, we can find the area A star that corresponds to the throat, corresponds to Mach number equal to 1 for that given flow. And this is true regardless of whether or not the duct is actually choked. So one way of saying this is that, so not all ducts are choked, but all ducts have a value of A star where they would become choked. So for any given duct problem, you can compute A star, but that A star may be smaller than the minimum area within the duct that you're actually looking at. So if the duct is everywhere larger than A star, if the duct is everywhere larger than that critical area, then the duct flow will probably be entirely subsonic. Could be entirely supersonic, but this is pretty rare because we're often starting from stagnation conditions at basically zero velocity. So the duct can everywhere be larger than A star, meaning it's generally entirely subsonic. Yes. Then there's something wrong with your upstream calculation. Yeah. Yeah, if the duct is everywhere or is in, yeah, it gets smaller than A star, then you have an invalid solution upstream. Yep. So for example, let's say that we're trying to solve a problem with variable area, with compressible flow through a duct of variable area. And we know that we initially have a Mach number of 0.2 at at an area of 1 meter squared, right, within our duct. And then we say, let's say we decrease the area down to 0.5 meters squared. So we decrease the area by a factor of 2. And I ask you now, what is the Mach number at that location, location in the duct where the area is 0.5 meters squared? One way to solve this problem, or a straightforward way to solve this problem, is to figure out A star, or figure out A over A star for that initial condition, right? Which you can do by looking up, the Mach number is 0.2, so you can look that up on the tables. Then decrease A over A star by 2. Right, decrease it by half. So you go from A over A star of about 3 to A over A star of about 1.5. And then look up what the Mach number is at A over A star of about 1.5. And you'll see that therefore, the Mach number at that smaller area is going to be about 0.5. That makes some sense? So and that could be the minimum area of the entire duct. But meaning that the flow in that duct would never become sonic, would never hit that Mach number is equal to 1. But you can still use this concept of A star in order to solve the problem. Jenna. So we have an equation relating A over A star to Mach number, right? So let's say we have, why don't we just work this out on the board? Give me 1 second. So let's say we're given this problem. We want to know so at this point, we know area is equal to 1 meter squared, and Mach number is equal to 0.2, right? And at this point, the minimum, we say that area is equal to 0.5 meters squared, what is the Mach number? Okay. So when you're first presented with this problem, we do not know yet whether the flow is choked through this duct. So we can't immediately say, for example, that the Mach number is equal to 1 just because it's a local minimum. Okay. So first we have to determine whether or not the flow is choked. So one thing, if we knew that there's a shock wave downstream, right? So if we said there was a shock wave downstream, then we know the flow here has to be Mach number greater than 1, and we know the flow here is Mach number less than 1. And the only way to get from less than 1 to greater than 1 is by going through 1, and then we would know that the flow is choked here. Okay, but let's consider this problem where we do not know anything else, right? This is all we're given about the flow. So, I'll pull up actually, we'll do it on the second screen. Let's see if we can get that back up. Okay. So let's go to our tables here. So at this first section here, at section 1, we know that the Mach number is 0.2, and therefore A over A star, we'll call it 3, 2.96. For this example, just to be simple, we'll call it 3. Okay. So at section 1, MA1 is 0.2. A over A star is approximately equal to 3, right? From the table, or you can also find that from here. So that means that we know that A star is going to be approximately equal to like 1/3 meter squared, right? So about 0.33 meters squared, right? So that's telling us that the area at which the flow would become choked, right? 4 conditions of area of 1 meter squared, Mach number 0.2, right? If we know those conditions, then the flow would become choked if I had a constriction with an area of 0.33 square meters. Okay, but we're given that the minimum area is only 0.5 square meters. So does this flow ever become choked? No, right? Because this area is greater than that critical area. Therefore, the flow is not choked at this throat. Yep. So the critical area is constant for the entire flow. If the flow is isentropic, the critical area is constant. That's a very good point. Shock waves are not isentropic. Shock waves will change the critical area. Shock waves will not change the critical area before. Yeah, shock waves only change the critical area downstream. Yes, yes, yeah, yeah. So, so if we have a shock wave, we'll see that it's going to change our A star. But for now, let's consider the case of isentropic flow, no shock wave. The critical area is going to be the same. Actually, I could have given you, for example, the flow conditions at any point throughout this duct, and you should come up with the same critical area of 0.33 square meter. Okay, as long as there's no shock wave. And when we have a shock wave, if we did have a shock wave somewhere, then A star changes just as we jump across the shock wave. So upstream of the shock wave, we would still have the same A star everywhere. Okay. Okay. So A star is 0.33 square meter. The A at the minimum here is 0.5 square meter. So the flow is not choked, right? But now I want to find the Mach. So the Mach number here is not equal to 1, right? Even though it's a constriction. So how do I find the Mach number here? What do I do next? Yeah.
You
What do you mean I have my original A over A star? Which
Have the A over A star equal to 3.
that's at this section 1.
Divided by 2 because you're having the area.
Mhm.
So I can see with A over A star 1.5 equals that amount.
Exactly. Right. So said another way, I know the area here is 0.5. I know the A star here, because this is isentropic flow from here to here. So I know A star, and in isentropic flow, we have the same A star. So we have isentropic flow from point 1 to point 2. So I know A star here is 0.33, right? So I know A over A star at this condition, about 1.5. And so now I can go to my table and I can look it up and I can see that my Mach number is going to be, somewhere 0.42 or something like that. I could find it by interpolation between those points. Okay.
And we shouldn't use the 1.5 value, the lower.
So why don't we use this value? We know that we didn't cross 1 because we know the flow is not choked and we're starting subsonic. So we're going to stay entirely on the subsonic arm of this table. Okay. Do you have a question? If the throat is symmetrical, and we have subsonic flow, so then yes, the Mach number would also be symmetrical, right? So if I then asked you, like if I have out here, I have A is equal to 1 meter squared. What's the Mach number? So what's the Mach number out here? If the area is 1 square meter, 0.2, right? It's the same as it was upstream. Okay. Now, if the flow is choked and we have supersonic flow out here, that would no longer be the case, right? But in this example, where the flow is not choked, right? Then we know we have subsonic flow throughout. Okay. All right. Any questions on this? Okay. So just to drive it home, let's say that let's change the problem. Let's say I still have area of 1 square meter, Mach number 0.2, and I'm going to tell you that the flow is choked. So what's the area here now if I tell you that the flow is choked? 0.33. Then we know the area is 0.33. And now let's say I tell you that there's a shock wave downstream, right? Actually, just from telling you there's a shock wave downstream tells you the flow is choked. But now if there's a shock wave downstream, what's the Mach number at this section where the area is 1 square meter? Has to be greater than 1, right? Because we have supersonic flow downstream now. So how do we find that? A over A star equal to 3. Yep. So look on the table. So roughly what number? Just give me a number. Yeah, 2.68, 2.65, somewhere in there, right? Somewhere between here is where I get to my A over A star equal to 3 for this downstream supersonic condition. Okay. All right, any questions on that? Okay. So that's going to be the general method of solving problems in this kind of a system. Okay, just basically, once you know your Mach number, we can use this table to find our conditions relative to stagnation. Right, so we generally want to know Mach number, right, if at all possible at any one of these locations. And we can use A star as a way of figuring out Mach number at each one of those locations. Okay. Okay. So we saw how computing A star was still useful for solving this problem, right? The initial problem where the flow was not choked. even though the flow never became choked, just knowing what A star is useful. And if the flow does become supersonic, then a shock wave can form, and we're going to deal with that really on Wednesday. So to continue our discussion, I do want to start getting into this of what happens as we change the conditions of supersonic flow. We're going to talk through what happens as we change through conditions of supersonic flow in some different cases. So we're going to consider, for example, a converging nozzle at the outlet of a reservoir. There are three pressures that we have to keep track of in this kind of a problem. The stagnation pressure, so the pressure like really far upstream where the velocity is equal to 0. We have to keep track of that. P naught. The exit pressure of the jet, PE. So the pressure that the flow is exiting our nozzle at, or our constriction at. And the outside pressure, atmospheric pressure, or we often call it the back pressure in compressible flow, PB. We're going to denote it as PB. For a subsonic jet, we said something about the jet pressure and the external pressure. What did we say? This is all the way back to chapter 3. For a subsonic pressure, they're the same. For a subsonic jet, they're the same. For a subsonic jet, the exit pressure is equal to the back pressure. But when we have supersonic flow, that's not always the case. Okay. So we have to keep track of all three of these things. So if we look at what happens, so this is now a plot of pressure relative to, so P relative to P naught as a function of X, as a function of distance in this system, as we move through this constriction. All right, so we'll see that we're assuming it starts at P naught, it starts at our stagnation pressure. We're assuming this thing starts out really, really big, so the velocity is basically 0 all the way at X equal to 0. And now we're accelerating the flow, right? This is a subsonic flow up until that exit there. And so we're accelerating the flow, and we see that the pressure is decreasing. And so if we have that pressure decrease, but only to a point where the flow is still subsonic, so the flow is not choked, then we're going to have a subsonic jet up at when the flow exits, and therefore the exit pressure is going to be equal to the back pressure, and we're going to have nice subsonic flow all the way through. But now if we keep, so let's say we're doing this by decreasing the back pressure. So we keep decreasing the back pressure, lower and lower and lower and lower. So from the subsonic condition, we're going to get to a point where we decrease the back pressure so much that we now have supersonic flow, or sorry, we have sonic flow. We have flow of Mach number equal to 1 at the exit. All right, so at this point, we would see still smooth matching from the upstream pressure P naught to this exit pressure. All right, so this is the condition where we have reached the critical Mach number is equal to 1 condition at the exit. So we have the exit pressure now is P star, exactly equal to the pressure where the flow is at Mach number equal to 1. But we could keep decreasing this exit pressure. And if we keep decreasing that exit back pressure, then now what happens is the flow still exits at P star. The flow still exits at that same Mach number equal to 1, right? This is a constriction. The flow cannot go beyond Mach numbers equal to 1 at that constriction. Meaning that for a given, remember, upstream stagnation condition, we have a fixed P star. We have a fixed pressure at that Mach numbers equal to 1 condition. So no matter what we do with the exit pressure, we keep decreasing the exit pressure, we cannot keep decreasing the jet pressure. So in practice, what happens is the flow will still exit at a pressure, which will exit at a pressure that's greater than the back pressure, greater than the atmospheric pressure. And then we'll see shocks and supersonic jet expansion and other things that happen downstream to cause matching of that pressure. The flow will still exit at the given P star. So as we lower PE, the flow will be subsonic until it reaches that critical pressure P star. At that point, it will be fixed at that exit pressure P star. From the isentropic flow relations, we can see that P star over P naught is about 0.5283, so about 0.5. So meaning if we had like 100 PSI as our P star, as our P naught, which is not that unheard of, then for pressures of less than about 52 PSI, 52.8 PSI, we would have a sonic jet exiting, okay? So and then at that point, the throat is choked and the mass flow rate cannot increase further, even if we keep decreasing that outlet pressure. So if we decrease it, if we had 100 PSI as our P naught, right, as our reservoir pressure, and we're exiting to atmospheric, right, then we're gonna have the same mass flow rate out as if we had a outlet pressure of 50 PSI, okay? All right. So we're gonna end it there for today. On Wednesday, we're gonna pick up and talk about flow through a converging diverging nozzle, and that's gonna set off our discussion of shock waves. All right, thank you all.